Yeah, they work for directed graphs. No, it will work perfectly fine for undirected also, because the only thing that will be, in fact, it's a little bit better for the undirected because you get a symmetric matrix. So the eigenvalues and vectors will still have interesting information. In fact, we'll see that not only can you use it for ranking, these eigenvector stuff can actually help you in clustering also. So whether the graph is directed or undirected only matters in terms of the, let's say for page rank type of a thing is more like how much of, because the direction matters in that case. But there are other networks where the direction probably doesn't matter. So you can still compute the page rank. It will borrow from everyone. So it's like, essentially every edge is an incoming edge. So in a way, there's a very deep connection between, these kind of models and even, Markov models and, neural networks for that matter. Essentially, they're all networks of some kind. And all you have to do is you have to define the rules of propagation. Right? So in a page rank of stuff, all you do is you take all the incoming edges. If they happen to be directed, a few of them will come in. But if it's undirected, all the edges will contribute. And you simply sum them up. Right? So it's a linear combination. In fact, it's just a direct combination. There's no weight. It's just incoming edge, weight 1, weight, the actual page rank value. But in a neural network, there is a value and there's a weight. So you multiply the value and the weight, you get a linear combination, and then you sum it up. And then the output of the network, in the page rank, it's just whatever value you get, you give it to everyone else. You divide by your degree. But in a neural network, you make a non-linear, change. You make a sigmoid function, and you output that. In a Markov model, in a hidden Markov model, you'll do something different. So each of these is some sort of a network propagation, flow propagation thing, but depends on what task you're trying to. So there's actually a very deep connection between all of these methods. It's just a different way of propagation. What you're trying to model, what you're trying to estimate. Any other questions before we move on to other things? Any structural? Okay, no other questions? Okay, so in that case, I'm going to begin this pattern mining. So this is our first encounter with the attributes. Okay, so far we've been talking about purely structure, right? So the graph is there, and we look at the degree distribution, the path length, clustering, and so on. But we did not really worry about the attributes. We did not say this node is labeled this way, this node is labeled that way. So pattern mining is one of those cases where actually the label actually matters. Right? So we're going to look at the label graph. And so in other words, we go basically from purely structured. This is pure structure. And this is of course structure plus label. So now you can see every vertex, right, has a label in it. Now this is still a very simple representation, so it's not able to capture all the information in the world, but it's still a fairly powerful model where every node has only one label, right? Like this node has characterized by B. This is labeled B. Maybe they are people who are connected to each other, and the label denotes some sort of interest. This person may be interested in, I don't know, in cricket. This person is interested in football. This one is the same cricket and so on. So this could be like a sports interest or in a graph among your friends. So these labels can mean anything, right? And generally speaking, even if you have more complex data, what you can do is you can always, you can flatten out everything into this kind of labeled graph. So if you think of a semantic network, okay, so maybe you have the data in the RDF format, the resource description framework format. So there, what you have is you have this triple. Okay, so you have a subject. So in real world semantic, knowledge bases and graphs and everything is stored in the form of a triple. And the triple is SPO. Okay, so what is SPO? Subject, predicate, and object. Okay, so S is the subject, O is the object, and P is the predicate. This is actually the label we are interested in. So normally what it has is that, supposing I want to know, this person, has, lives in the city, phone number is that, interest is this, right? So each one of these will become a subject-object link, and the predicate would be lives in, phone, and so on, right? So those kinds of things can, so essentially all kinds of relationship networks, we can add labels to the edges. Here I'm not showing them, but each edge can be labeled, each node can be labeled. Right? So even very complex semantic graphs can be laid out, and they can be represented by these labeled networks. So now the question is, you have this huge interconnected maybe network with all kinds of labels, attributes, and so on. One of the key questions is, what are the patterns? Are there hidden relationships, hidden patterns in this network? So pattern mining is really about finding interesting subgraphs. So in this, so let's say if I have this network, I say what are the interesting patterns you might observe. So one thing might be, for example, a simple edge, for example, right? So AB. Okay, so there's an AB here. There's one edge AB. There's another edge AB. So there are two edges AB. It's not that interesting a pattern, but it's the simplest sort of edge-based pattern. So there are two instances of the AB pattern. Actually, no, there's three. So there's this one also. A and B is connected, right? So, and there may be more if I have to enumerate them, but at least those three are there. So the AB edge, there's an AB edge, an AB edge, and AB edge, right? So the pattern AB, normally what we do is, you have some sort of a pattern that you want to, so the task in, the kind of method we're going to look at is that we don't know which pattern we're looking for, okay? So we have to enumerate all the patterns that exist. But let's say if I have a pattern, then I can find out where all it, matches. So here I will say AB matches at V1, V3. It matches at V4, V3, V7, V4, V7. And maybe that's it, right? So this would have sort of three occurrences, if you will, three instances where this matches. Maybe you have bigger pattern. Maybe you have a pattern like ABB. Okay. So what about the pattern ABB? So I can say, what about A, B, and B? So that would be V1, V3, V7 is one example, right? V1, V3, V7. Of course, V4, V3, V7, and so on. So the idea is that, whatever pattern that you want to sort of find, you also have to count. You have to sort of find out where in the graph it occurs. Okay, so this is an extremely challenging problem, because in a graph, you have to, because as I said, I don't know which pattern I'm counting, so actually I have to count all of them. Okay, so I have to enumerate combinatorially all the single edge patterns, all the patterns with two edges, all the patterns with three edges, four edges, five edges. We keep on going and going till there's no other pattern to be found. And the way we sort of look for the goodness, if you will, is how many instances do you have? Okay, so how many matches do I find? So here I have to put some sort of a cutoff. I have to say that, so if I say that the number of matches should be 3, then, if I find a pattern which has less than 3 matches, then I can throw that pattern away. So only those patterns that appear at least a certain number of times, they will be kept. This is the notion of a frequent pattern mining. So there is this sort of a cutoff value, and we basically say, so we want to find all the patterns that occur above that cutoff value. So that means it's a frequently occurring thing. That means it might mean something, and we can sort of use that information for many applications. So there are two kinds of mining tasks. Before I go on to the actual, formalize some of the concepts, I just want to give an idea for the kind of applications. So there are two kinds of graph mining problems. One is where you have a single graph. this is the kind of stuff we've been talking about so far, like a social network, or a biological network, or an eco network, right? So it's just one large network that's interconnected. It's extremely large network, right? Billions of nodes and edges. But you have just one graph, okay? So here's one graph, and you have the connections. Okay, so that's on one side. So now you have to find the frequent structures, or frequent patterns actually. So pattern will always be a combination of the structure and the label, right? So they go hand in hand. So here you have to find the frequent patterns in one graph. And this is a little more challenging, and I'll tell you why in a minute. But the other side is, you have lots of graphs, and you have to find a common pattern in many, many graphs. Okay? So here, what you have is, you have many smaller graphs. It's more like a graph database. They're all labeled, of course, A, B, A, B, A, C, A, B. These are also labeled A, B, A, C, A, C, B, A. Whatever. There's some labels on these networks. But here's graph number 1. Here's graph number 2. Here's graph number 3. And let's say G3. And typically there are many, there are possibly millions of these small graphs. Now this kind of data sets happen in chemistry. For example, what you do is you take the drug compounds, and each one of those compounds is a small graph. You can actually represent the chemical compound as a graph. And you have one compound, another compound, literally millions of them. And these pharmaceutical companies, when they do drug design, they have to sort of test the properties of these, because you're making new drugs, and each one of these chemical compounds has certain properties. So let's say if you want to do a drug targeting some disease, let's say cancer, for example, certain of these chemicals would be found to be effective in sort of maybe subduing the effect, right? So the idea then is that they try to mix them and match them. So they go through this whole set of million different compounds, and they sort of study what happens if I do that, what happens if I do that, and it's kind of like what are the common properties among them. So you have to look for these common features. So that's one of the applications is in pharmaceutical industry, in drug design and drug discovery. This also happens in other, like each of these could be like a user browsing session. So let's say if you're a portal site, Amazon, Flipkart, whatever, people come, they buy, they browse your website, they end up buying something. So each user is basically modeled as a session, right? So you get the user web crawling sessions. So that's user number 1, user number 2. Now you have millions and millions of users, and from that you want to learn certain patterns. Like how do people browse my site? What do they end up buying? So you can do that. Third thing you can do is that you can actually go from this graph to this graph by building ego networks. So the idea is that for every node, you do a 1-hop or a 2-hop, local network around that. And so this becomes like a node-centric network. Right? So every instance is basically a blow-up of this one, but the local neighborhood. So I can pick this node, and if I say just 1-hop, you'll get star-like pattern. But you can also keep you can sort of complete it, right? So any neighbors who are connected, you can also connect them. So extract the subgraphs that are within a certain number of hops away, and connect all and then do a closure of that. So from a single large graph, you can go through and so this would be like an egocentric. So ego basically says that from a perspective of a single node, do a 1-hop, 2-hop, whatever number of hops you want to do, and create the subgraph around that. And now you get many, many different graphs, and you can analyze those to see are there common patterns among the neighbors of people, right? So this an idea is very useful. For example, Facebook wants to do social search, where they want to recommend new people or new products or new things based on who your friends are and how they basically interact with each other. So this has the same, and then LinkedIn would do the same thing for professional networks, right? You want to suggest new colleagues you might want to connect with. So you can do this sort of egocentric analysis and then look for the common patterns that way. So these are the two sort of spectrum that you either have a very large graph or you have lots and lots of graphs which are generally smaller, but you have millions and billions of them. So in this network, one of the key things is that we have to enumerate subgraphs, right? So the idea is a pattern is basically a template. Right? So it is some sort of a structure with some labels. So a pattern could be something like, A with a B and a C. Do you find such a triangle, for example? This is my template. So what I have to do now is I have to go to the network. Like if I look at the single large network, I have to see, in this entire network, do I see such a triangle where, so this might be a very unique, combination. Maybe some guy is interested in cricket and football and squash, whatever, they're very close friends. Do we see this happening many, many times? Right? So, and maybe there's a trivial example, but the idea that, this might mean something in more interesting applications, and especially for recommendation in social search and so on. So I can look for these patterns, where do they appear, if at all. So in this network, I don't find any instance of that. So even the absence might mean something, right? So if you look at a real network, and you think that this sort of connection should be there, and you observe that there are no such connections. So then the question is why, right? And this sort of makes a lot of sense in biology and other types of phenomena where you think that these things should be related and they are not. So that might, even the absence of certain patterns can actually convey some interesting information. So this is the pattern, this is the template. But what you have to do is, so first of all, this is unknown. Okay, so we don't know which one. So you technically have to generate many, many of these patterns to begin with. But once you fix one thing, once you say this is the pattern I want to count, the next task is you have to find the matches. Okay, so those matches, I will be using lots of different terms for those. So for any given pattern, which is a template, the actual subgraphs in the input, they are called isomorphisms or embeddings. Okay, so I will be using the word matching, isomorphism, embeddings. They all are going to mean the same thing. That is, for this pattern, I need to basically put it somewhere and see whether it matches or not. Put it somewhere whether it matches or not. Every time I get a match, the frequency goes up by 1. So because I need to know how many times this pattern is observed. So you basically go around counting. And this is basically, as I said, it's essentially a subgraph isomorphism task. And subgraph isomorphism is an NP-hard problem. Okay, so, and we want to do this millions and millions of times. So it's like you're taking an NP-hard problem and you're amplifying the complexity of that problem even more. Now, of course, it's an NP-hard problem, but it doesn't mean that we cannot do interesting things in practice. Because normally the patterns we're trying to look for are small. Okay, so that means there is still some hope in actually, because if the pattern that you're trying to look for is extremely large, then you're going to have trouble with the real complexity of the solution. So here we can do many, many clever tricks to prune the space, do more efficient search. So yeah, theoretically it's an NP-hard problem, but practically there is still many interesting applications, many interesting algorithms we can come up with that tend to work well in practice. And I'll show you some examples where they do not work. And when they do not work, you can do sampling. Because I'm going to show some ideas about sampling the pattern itself. So we can actually, there is a lot of hope in actually doing this in practice. So anyway, this is the point. The problem is that you don't know what the patterns are, so you have to find out all patterns. You need to, for any given pattern, you have to find out all these things. Basically, the isomorphisms, which are also called embeddings or matching. So find all the matches, count them, and then you use the notion of support. Okay, so there will always be this notion of a minimum support. So this is your minimum frequency. So anything below this we can throw away. Okay, so that's the key way in which we prune the space. Because if you didn't have that constraint, then there is, there would be no hope. You would not be able to actually mine anything beyond very small, very, very, very small graphs. Now, how are these two problems different, right? So you might ask, why are they different and how are they different? Well, the problem comes as follows, that when you have many, many graphs, and I want to know the frequency will be how many graphs contain this pattern, okay? So even if there's one instance, the count goes up by one. So in this scenario, where you have many, many graphs, the support is the number of graphs. Okay? This is the min sub. So I'm going to be using this notion of this minimum support is abbreviated as min sub. So min sub will be, or rather I should say the support should be, support of a pattern P will be the number of graphs that contain it. Okay, so this side is easy in the sense that, you know, I look for a pattern. Even if it appears once, the count goes up. It may appear 100 times, but I don't really care. Okay, so in any given graph, I'm looking for one instance. I do not have to enumerate all the instances because it's whether or not the pattern is in G1, whether or not it's in G2, and so on. So every time I just do a binary check. Is it there, is it not there? And so the support is simply how many graphs contain it. But on the left, there's only one graph, right? So here the problem is that what is your minimum support? It's not the number of graphs because there's only one graph. So here, unfortunately, you have to enumerate all the instances. Okay? And then you have to do some sort of a support based on all the instances. And that's where the real problem comes. When you try to enumerate all the instances, there can be exponentially many matchings. Okay, so to give you a very quick example, supposing you have a graph like this. Supposing you have a graph where there's a single node A is connected to maybe 1,000, Bs. So there are 1,000 Bs. Okay, so all of these are Bs. Okay, now each of these Bs, let's say, is connected to 100 Cs. Okay? C, maybe 100 of them. So now if I ask you, right, how many matchings of A, B, C do you have? There are basically 100,000. Okay, so A, B, C is a pattern, and there are basically 100 times 1,000 matches, right? Because starting from the same A, right, I can follow any one of these Bs. Any one of the Bs will let me go to 100 Cs. So you can see that, if you start counting all the embeddings, very soon you're going to be in trouble, right? In a real world network, if you have this kind of behavior. Fortunately, this kind of behavior does not happen all the time, but it can happen, right? If this is a hub node, right, and the hub node is connected to a million other people, and those people are themselves connected to many other things, then you can see how quickly the number of possible matchings or embeddings or isomorphisms will blow up. So this is a real issue in a single graph. Okay? But there is a trick we're going to use. So in a single graph setting, what we do is we don't actually try to enumerate all the embeddings because they are possibly exponentially many. And they're all, like in this case, they all start from that 8, right? So essentially, one can do some sort of tricks and say that actually you can look for, so here the notion of support can be all the embeddings. Can be the number of embeddings. And this is a little bit of a problem because they're exponentially. Okay, but then another very profound problem with this notion. Okay, if you look at the support, okay, how many times does the label A happen? A happens only once. Okay, so the support of A is 1. I mean, in this particular example, right? Okay, how many times does AB happen? Okay, so support of AB 1,000, and of course support of ABC, as we said, is 100,000, right? This is a real problem, that a smaller pattern, normally speaking, the more general you are, the less, the more frequently you should happen, and the bigger you go, your frequency should go down. Okay, because as you grow, in a normal situation, like in sets and other types of problems, you want the frequency to decrease. As I find larger and larger things, they should happen fewer and fewer times. But here we have the reverse trend, that actually the larger the pattern is, the more it is appearing. So this is called this property means that we cannot prune the search space, right? So because I'm counting and I'm trying to cut off, if I say A happens 1 and I cut it out, I say remove the A, then I will never find A, B in the other thing, right? So in other words, you cannot really prune A. If you're using this definition and you want to know all the embeddings, you're basically stuck. You can never ever prune the space because you don't know what's going to happen next. Of course, when I say never ever, I mean you can do some smart things and see are they neighbors and what the labels are. But generally, you have to try many possibilities. So this becomes extremely expensive to compute, even from just conceptual point of view. That you don't have a nice definition that allows you to prune the space effectively. So here, instead, what we do is we say that the support can be defined by the anchor node. Okay, so one trick is that I'll say that this pattern also appears only once. And the reason I say it appears only once is because there's only one real anchor here. Okay, the starting point is still only one. So yes, there are many, many different emanations from that. So we can change, so in other words, we can use a different definition. Okay, the definition would be, if you really want this, what we call the monotonic property, that a larger pattern should have less support. So it's called the anti-monotonic property because the support decreases, or the support never increases rather. So we can say that actually we are going to define support to be the number of matches for the least number of matches for any node. Okay, so that's a very good definition of support. So support can be defined as, over all the vertices, it would be the minimum over all V belonging to the pattern P. And this will be the minimum of the number of matches for V. So now we're taking the minimum over all the patterns V belonging to the pattern P, right? So if you look at the mappings for, if you look at the mappings for C, there will be 100,000 mappings for C, okay? Because each one of the V's in it has many, many mappings. The mappings for B, there will be 1,000 mappings for B, but the mapping for A, there will be only one. So when I actually look at the actual matches, I'll find that the minimum is for the A, and the minimum is only 1. And so I will say the support is actually 1. And so this then preserves the pruning power. So then I can actually prune things. So whatever, one, of course, with one you cannot prune anything, but if my minimum support was 10 or 20, that means if you don't appear 20 times, I'm going to prune you regardless. And that will keep the correctness of the method intact. So you have to sort of be a little bit careful about what you mean by support, how you count. And the single graph situation is a little bit more challenging. So I'm going to focus more on the multiple graph situation, but the method, the algorithm can handle both. Okay, so we will see that it's easy to go from one to the other. You just have to change the definition of minimum support. The minimum frequency is all that changes. The rest of the method will be the same. Alright, so this is the task. So the task is you're either given a single graph or you're given many, many graphs. You're given this minimum support value, and you have to find all the subgraphs that appear at least that many times. That's the mining task. Alright, so this I think is formalized, I'm not sure if it's here. Alright, so this is the definition. The frequent subgraph mining problem is, so as I said, I'm going to start with the case where you have many graphs. So you have a database, okay, and a database has n different graphs, G1, G2, up to Gn. For this case, the support definition is given as follows. The support is simply the cardinality of the set, and all this says is how many graphs in the database contain my pattern G. Okay, so G is a pattern or a subgraph, and Gi is some graph in my database, and all I'm saying is how many times is G a subset or a subgraph of Gi. Just count all the numbers. And then we say that a pattern is frequent, G is frequent if the support is above minimum support, above min support. So if there's only a single graph, I'll just change the support. Okay? So I will just say this is not this, it's actually for everyone it would be not the number of graphs, because there's only one large graph to begin with, it will be that minimum anchor support, right? So the number of matches for the least number of matches across all the nodes in the network. So once you make that change, the rest of the statement remains the same. You're still looking for frequent patterns. Alright, so that's that. So that's the task. So now let's define a little bit more formally what we mean by isomorphism matching. So the isomorphism problem is actually, this is just to make sure that mathematically we understand what we mean. You're given, if I give you two graphs, okay, I give you G prime and G. Okay, so G prime is a graph, V prime, E prime, and G is some other graph. And this is basically, we want to test whether they are equal or not. This is not even talking about subgraphs. This is just saying, are the two graphs the same? This problem, by the way, right now, if I give you two graphs, G prime and G, and I ask you, are they isomorphic? Meaning, are they exactly the same graph? This problem is, there is no polynomial time solution that is known to this. Okay? That means people think this problem can be solved in polynomial time because I give you the whole graph that's all the same size and everything. And I just need to make sure that the edges and everything match. But as of now, we do not have a polynomial time algorithm to solve this problem. So even this problem is actually hard. Although there is a very, very recent progress. So if you follow any of the recent news, so very recently, a professor from University of Chicago, he has shown that this is almost polynomial. Okay, so that means, theoretically speaking, it is not yet polynomial, but it's almost polynomial. That means it can be done relatively fast. So anyway, but that's the problem. So we're saying, are the two graphs equal or not? So what should you do if you want to see if two graphs are the same? So we say, are they isomorphic? Well, what you have to do is you have to find a one-to-one and onto function, right? An into and onto function, where if for every edge in G prime, the map, so phi is this function. Okay, so I have to match. So basically, pick a node here, pick a node here. So let's call this node 1 and node 2. There are two other nodes here, node 10 and node 20, for example. So maybe one will get mapped to 10, two will map to 20. And let's say there's an edge between these two. So if you were to think of this mapping, right? So I don't know what the mapping is, but if you could, so we have to find that mapping. Okay? So if there exists a mapping where for every edge in E prime, there's a corresponding edge in E. Okay, so that edge must exist. So obviously if I map this way and the edge is not there, the graph, that's not a valid isomorphism. It's not a valid mapping yet. But if this edge exists, then at least that edge matches. But then I have to continue. You're not done yet. So you have to keep on doing this. So what this says is that for every edge in E prime, the mapped edge should be in E. The next thing is that the labels should match, right? So the label of the vertex here should match the label of the vertex there. And thirdly, if the edge has a label, the label of this edge should match the label of the matched edge. So all the labels and all the edges should match. So that's, and everything should be covered. That means no vertex should be left unmatched. So of course the graphs have to have the same number of edges, the same number of nodes. And then you have to find this matching. Right? So as I said, it looks like an easy problem, but it's not actually, there is no polynomial time solution for it. So that's what an isomorphism is. Basically preserve the structure and the labels. Okay, so that's whether two graphs are the same or not. But what we really want is whether one is a subset of the other, right? So then the only change you have to make is that you remove the onto part. That is, G prime can match a subgraph of G. So every edge in G prime should be in some subgraph of, G, but it doesn't have to cover all of G. So G can be much bigger. So maybe G is actually, this is the actual G. And you find a sub-pattern within that where you can match. That would be a subgraph isomorphism. So G is much bigger and you're finding a match. So that's the task. That essentially everything, at the end of the day, boils down to isomorphism. That is, for any given pattern, you have to check, you have to find these mappings. If you can find even one mapping, that's a good thing. but generally we may have to enumerate all the mappings, right? So in the single graph case, you have to generate many mappings to see. So this mapping is called the isomorphism, the embedding, all those terminology that I've been using. So here's an example. So here I have a database of 4 graphs, G1, G2, G3, G4. And each one of them kind of looks different. So for example, I think these 2 graphs are the same. So if you look at this graph and that graph, right? Essentially, if this edge, if I turn it around that way, make it from here, it will be similar to this one. So if I want to know the isomorphisms from G1 to G2, whether it's full isomorphism or a subgraph isomorphism, I can list out all the matches. So in this case, it turns out that there are 4 matches between G1 and G2. And I can pretty much list them all out. So I use these, So the first one says that essentially just map from V to U, right? So it says, so basically I'm saying G2 to G1, okay? So obviously this can match. I can match this to this. I can match this to this, and I can match this to this, right? So that's one isomorphism. So one matching, and that isomorphism is listed as this one here, the first one I think. So V1 matches to U1, V2 to U3, V3 to U2. Yeah, V actually is the other way. Yeah, this is the other way. V3 to U2 and V4 to U4. So that's the matching, the first one. But of course, as you can see, you can interchange the bottom 2 without any difference. So instead of this matching, I could have also done this. This can match this and this can match that. That is still a valid matching. It preserves all the labels and structure and so on and so forth. So it turns out that there are actually 4 of them, and these are all the 4 matchings. So, but this is the task that we have to, if I want to count, then I have to enumerate these and then, find out the support. Okay, so that's the matching isomorphism, and one can talk about subgraph isomorphism the same way. Alright, so now comes the actual mining problem. Okay, so there's a lot of sort of terminology here, and it's going to take me a long time to actually go through everything. So what I'll try to do is, I'll try to give you the intuition, but I'll work through all the steps. Okay? And the way I'm going to work through all the steps is, so I'll come back to these concepts, but let me start with an example first. And I'll illustrate the idea on the small example. So this is my database. Okay, so this is a database that has 2 input graphs. Okay, just 2 graphs. Okay, my goal is to find out all the patterns that exist, and I'm going to even say that they must exist in both. So I'm going to say minimum support is 2. So the question is, how do we start and how do we start mining this? How do we start mining this database? All right. So the way we're going to do this is, let me make a few insert a few slides here. And let me copy this here on the top so that we know what we're talking about. So we have A, B, and then we have labeled the vertex number 10, number 30, number 20, number 40, 50, 60, 70, 80. Okay, I want to have more space, that's why I'm writing it out here. Okay, so this is your database D. This is G1, this is G2. Okay, so now we have to start the mining process. So the first thing you should do is, we start with the empty graph. Okay, so here's my empty graph. Empty graph by definition appears everywhere. So the support is 2. Okay, so, and I'm going to say minimum support is 2. So trivially, the empty matches everything. It's a subgraph of every other graph. So the support is 2. So anyway, that's just our starting point, we don't really care. But the main point is that I'm going to do edge-based expansion. Okay? So I'm going to do one edge at a time. So what I can start with the empty graph, and I can add one more edge. Now here's a little bit of an interesting thing. So first of all, you need to know how many labels there are. Okay, so you have to have a label set. Sigma is your alphabet or your label set. And in this case, in this small example, there are really only two symbols. So this is your alphabet. So there are only two labels. So how many single edge patterns can I have? So the idea is I need to enumerate the templates, the patterns, and then I need to match, right? So how many two edge patterns can I have? I'm sorry, how many single edge patterns can I have? I can have, so let's put I need to have an edge, right? So the question is, how many choices do I have for the first? How many choices do I have for the second? There are two here, there are two here, right? So there should be four. So the four should be AA, right? That's the pattern. How many times is A connected to A? Another would be A connected to a B, right? Third would be a B connected to an A. And fourth would be a B connected to a B. And those are the only four choices I have, right? There's only a single edge. So it's really essentially sigma squared, right? So whatever the alphabet size is, this is how many different possible patterns I can have. But there's one thing you should notice here. What you should notice is that AA is fine, BB is fine, but these two are isomorphic to each other. Right? Whether I say AB or BA, does it matter? I mean, the edges are not directed here. So it's an undirected pattern. If it were directed, things would be different. Okay, so I'm assuming I'm doing undirected mining. So the AB and the BA, there's no difference. But I don't want to count the same pattern twice, right? So one of the key things in the enumeration process is you have to be able to detect duplicates. So I should be able to say, one of them I'll keep, the other I'm going to throw away. This problem is called canonicality testing or duplicate testing. And I'm going to basically throw away this pattern. Okay? So I'm going to say this pattern I'm not going to count because I have another pattern that is the same, and it is what I call canonical. So this, I'm going to explain this term in a little bit more detail, so that it's what the key. So first thing is duplicate elimination. And for this we do canonicality testing. Okay, canonicality means that I have to be able to come up with the total ordering. Okay, so given a graph, I have to come up with the total order so that I can compare two things. And then I can just go one by one and do a lexicographic comparison. Like say, one, are they equal? Are they equal? Are they equal? Is one less than the other? That means this is smaller than this, and I'm going to throw it. Okay, so here, the basic, I'll go through the formal definition shortly, but the basic intuition is that if you have a node labeled with a smaller label, okay, that is preferred over a node with a bigger label. So because AB begins with the A, as opposed to beginning with the B, right, the BA, so we prefer the AB route. Okay? So if I just compare them and say, I mean, this may not be immediately clear, but I say the A is less than the B, and of course it is the same pattern. I mean, so you I'm assuming that it is the same for now, but I'll show you how to do this independently. So, but for the time being, is basically because this begins with an A, I'm going to keep this as the canonical representative. Because if I need duplicate, only the least member will be kept. It's called the canonical member. And we use this notion of, which I'll define later, it's called minimum DFS score. So this is something that we use to represent the canonical member, the least member. And I'll go over this notion later, but intuitively this is what we're doing. So we need this minimum DFS code. So when you look at the code for this one will be less than the code for that. So it's essentially you're coding up a graph as a linear string, and then I can just go down the string and do a lexicographic cascade. Okay? Alright, so these are the three patterns we have to count. So I can now go and count them, right? So you do the subgroup isomorphism and things. So you say, okay, how many times does AA happen? Okay, so it's like 10, 30. But it could also have been 30, 10. Right? So there's no, right? Because it's an AA pattern, whether I begin with the 10 and the 30 or the 30 and the 10 doesn't really matter. So it's still a match, and there are two different ways of matching it. Okay? 10 to 30 or 30 to 10. It's an undirected edge, so they both count. So the 10 and the 30 are just some global labels. They don't really have any meaning other than identifying the nodes. What really matters is the label of the vertices. The actual global ID is immaterial. The global ID is just to distinguish every node from every other node. So that's why I have to keep both. Because when I say AA, it could be this AA, like 1030 or 3010. So I keep both. So there are really two matches. Sorry? Oh yeah, this one I will explain later. So, but the point is that this minimum DFS code is basically a way of taking a pattern and representing it as a string. Right? So the graph is, all pairwise things, but I need to have some sort of a way of encoding it so that I can compare two graphs and test which one is less than the other. So to give you an idea, actually, the depth first code actually is simply, it takes the graph and it goes in a depth first order. So this is node number 1, this is node number 0, node number 1. And this pattern will be represented as a tuple. It will be represented as 0, 1, 80. This will be called the code. Okay? So 0, 1, 80 basically says that node number 0 in the pattern is connected to node number 1. And the label of the first one is A, the label of the second one is B. And if there was an edge, the edge label, I will put the edge label here. So right now I'm ignoring the edge label. So that's how I code up the pattern. It's a depth first coding up. And the code for this one would have been the 0, 1, BA. Because the 0 and the 1 is simply a depth first numbering. Okay, start from the root. You say root is 0, the child is 1. So it's always 0, 1 for the first edge. But then this is BA. And then I can compare these two, right? So these two tuple I can compare to each other. I can say this is 0, 1, 0, 1. But this is an A, this is a B. So that means this code is smaller than that code. So that means there is a way of testing whether one is smaller than the other. And this allows me to prune certain patterns because they're duplicates. So I will go more into the actual, because it's a little bit more complex than it appears here. But basically I can look at a pattern, and from that pattern I can tell you whether or not that pattern is minimal or not. So we're not done with this AA yet, so you have to count. So for any given pattern you have to count, and so then there will be 60, 80, and 80, 60. So we have all of them, and that's it. So this happens, and now this happens in G1, this happens in G2. So the total support is 2. So because again, remember the support in this case is how many graphs contain it. So both of them contain the support is 2. So in fact, all of them, probably, except for the BB, the BB doesn't pass. And I can just tell you because there is no B and B edge here. So the support of BB will be 1. So I'm not going to go through the whole step. So it only appears in G2. It doesn't appear in G1. So this we can throw away because it is not frequent. So you can basically come and say, this is not frequent. And this one was thrown away because it was not canonical. So there are two steps, as I said. There is the duplicate elimination step, and then there is the counting step, right? So that's all there is actually. I mean, in terms of conceptually, then there is the counting, the subgroup isomorphism counting. Okay, so these are the two key steps in graph mining. Okay, so anytime I generate something, I have to remove any duplicates, And then once I have a pattern, I have to go and count. And if it is above minimum support, I keep it. If it is below minimum support, I throw it. And so now, two of them will survive. The AA and the AB will survive. So I have to do the next step. Alright, so what can I do? So let's start with AA. Let's start with AB. So here's the pattern, which I know was frequent. Okay, so it was frequent from the last step. How do I extend it? Okay, so this is part of the iteration process. So how do I take this pattern and extend it by one more edge? Well, there's only, there are only two endpoints here. Either I can start. So remember, in the depth first ordering, which I haven't yet gone through, but this would be node number 0. This would be node number 1. So there's always, what we do is we put a depth first tree-like structure on a graph, okay? And we're going to be using that tree to do everything else. And the tree will become clear as I go through. So right now there are just these two nodes. This is the root, this is the child. Root is 0, child is 1, and it's AB. So how can I extend it by one more edge? The edge can be from the B, or the edge can be from the A, from the 0. Right? So there are really two templates one can have. You can either have this, or you can have this. Right? These are the two possible choices we have for the next type of pattern. Now I put a question mark here on purpose because I have to look at my alphabet, and it could really have been any one of those. It could have been an A or a B. This can also be an A or a B. So however many choices I have, because I don't know which label might be in my data set, I have to enumerate all of them. So actually there are four choices. There will be 4 in this case because my label set is only, so there will be 1, there will be this one, this one will be the A, and this one will be the B. Right? So these are my next choices for one more edge. Okay, so now comes the interesting point. Okay. And let's do also from the A because I want to illustrate a point here. So there will be 4, so starting from this one, there will be again 4 extensions. There will be A, B, and B, right? So these are all the patterns I can have in the next level because these are the 2 patterns that were frequent. So these are 1 edge pattern, frequent pattern. So these are all the possible patterns I can have for the next step. Alright, so now comes the interesting point. There are lots of duplicates here. Right, so let's see if we can find a few duplicates. Okay, so this might not be immediately clear because it's a little bit squiggly over here. Actually, let me write this a little more clearly. A, okay, so look at this pattern. This one? Here?
Yeah.
This one?
This is
Good.
Okay.
Right, AAB. Good. So at least we have this one. Is there anything else? Actually, even this one, right?
Yeah.
Right. It's the same pattern. AAB. So that's AAB. This is also right. So remember, so this is graph isomorphism. So the way it is shaped doesn't really matter. The structure should be preserved. So this is AAB, but this I can also read as AAB, right? The same thing. And this is also put AAB, right? So I think that's it. So for this pattern, there are three things. Only one of them can be canonical. Okay, so now I'll explain the canonical part. How do I do the canonical check?
First and third also, second.
ABA.
This one?
Second.
The next line is this one.
This
Yeah,
one.
this ABA. ABA.
But the ABA is different from AAB.
Third one.
Oh, you mean there are more duplicates? Yeah. So I haven't done all of them. Right. You're right. So actually they're going to be here. So let's put this in red. Right? So this is, these red patterns are the same. But if you do more, yeah, you'll discover many more duplicates. So for example, for this blue one, let's say BAB. So is there any other BAB? BAA, no. So this one is unique, that's fine. ABA, right? ABA. Let's see, where is it? For this one, can you find something? No, this is also fine. ABB. No, there's no ABB. Okay, but this one. This and this is the same. Yeah. Right. So those are duplicates, I think. Everything else is not a duplicate.
Second and fourth. ABB. In first block.
Sorry, in the first one? Yeah, second and fourth. Oh yeah, good. So that's the third one. Okay. Okay, so these are the duplicates, right? So think of these as three groups of patterns. Anything else?
So it's BAB and AB.
BAB and AB.
No, the structure is not the.
So BAB. Okay, that's fine. So that's different. So is there anything else? So this is not good, right? Okay. So, well, we may have missed something. I'm sure. But let's say this is, it doesn't really matter. I mean, there are probably many. I mean, perhaps there are other duplicates. But the point is, among the red ones, only one can be minimum, and among the blue ones, only again one can be minimum. So we have to remove the rest. Now, I don't want to compare. Okay, so if you start comparing, it's going to be a problem. So I cannot say I'm going to test this and test it with that, because I don't know which are the red and which are the blue. So if you start comparing with everyone else, you're going to be in deep trouble. The test has to be local. It has to be with respect to the pattern itself. Okay. But let me tell you the intuition first, and then I'll explain how we do it. Intuition is we want patterns that are deeper as opposed to more branched. Okay, that's one principle. So this is just, I mean, you can define any ordering as long as your principle, but the one I'm going to follow is a deeper pattern is preferred over a branching pattern. So in fact, this red will be the one that will be the minimal one. Okay. So the AAB, that is the rightmost, is the minimal canonical form. This one and that one are not canonical. So I'm going to say that I'm going to throw these away. Okay, these two will be thrown away. This is the canonical form for this. Right, I will use red. So this one is canonical. This one is not canonical. This one is not canonical. And then for the blue, the same idea will apply. This is the canonical form. This is not the canonical form.
Can you explain again why it's not?
No, so now I'm going to tell you why. So the intuition is that a pattern that is deeper, okay, so we prefer depth over breadth, right? So this is of course deeper, right? It has depth 2, this is depth 1. This is also depth 1. So you prefer, if you could have the same pattern, the deeper one, the one that has more depth will be preferred, over the one that has more breadth. But that, I mean, this is it's a pretty vague thing I just said. So I have to make it more precise. But let me tell you how we do it. And this is actually a key point. What you have to do, and this is why graph mining is such a hard problem. So I'm going to start with this one, okay? I have to be able to determine whether or not I am minimal, I am canonical, without looking at anyone else. I cannot look at other patterns, but I can do something with my own. So here's how we do it. So I start with AA and B. Okay, this is the one, and I have to just ask the question, is canonical? Okay, so I have to check, are you canonical or not? So this is all I have. Okay, now in this pattern, I haven't told you about the depth first tree, but every pattern comes with a depth first, structure. So this is labeled 0, this is labeled 1, this is labeled 2. So this is a depth first numbering. So first you follow this edge, you come back and you follow that edge. Okay? So 0, 1, 2 tells you the depth first order. So every pattern has a depth first ordering of the nodes, because the way we grow it will be in depth first order, as I will show later. So this is the depth first ordering. So this has a representation. So now what I have to do is I have to put the, in my tuple form. So remember the tuple form I said, first you pick the first edge and you write it as a tuple, 0, 1, AB. And then the next edge would be 0, 2, AA. Okay, so this is called the DFS code. Okay, so the DFS code is very simple. If I tell you the depth first tree, you can give me the code. With just every edge in depth first order, you pick and you write it as a tuple. So this is what is called as the code for that. Okay, now I have to basically, the question that I'm asking is, can you find a different code that is less than this one? Okay, so that's the only question you have to answer is it possible that I can come up with a different pattern, a different code that would be less than the code I have? So this code is fixed, right? It's for this pattern, this code is fixed. Alright, so, but you do have the structure, right? So, and I know that A is less than B, so I have a lexicographic ordering of the label. So I'm defining that the label A comes before B. Okay, so A is less than B. So that we know. Now what I have to do is I have to sort of think the whole thing in this following manner. I have to say, supposing I erase these depth first numbers, right? Because this is what was fixed, this is what you gave me. But I don't have to follow that, I could follow anything else. And there are many, many depth first trees I can construct. It's not only one depth first tree. So I'm looking for a depth first tree that will lead to a smaller code than this one. Can I find such a tree? Okay, if after trying all possible things I cannot find it, that means I have to be minimal. Okay? But if I can find something smaller, then obviously this is not canonical, right? So that's the basic idea. So let's see, now that I've told you that A is less than B, and for the time being, I'm basically going to pretend as if the labels do not exist. Okay? There are no numbers. You are free to choose the numbering totally on your own. So, where should you choose the numbering? You might say, okay, let's begin with this as a 0, this as a 1, but that would be a bad choice because you should never begin with a B. If there is a node labeled in A comes before the B, so you should always start with a node labeled A first. So that's not any good. So you might say, let's make that 0 and let's make that 1, which would be fine. So that would be one choice of a depth first. So then this one will become label 2, right? So if you do it the other way around, once I've followed this edge, then I have to follow that edge, right? And so the code for this one would be what? The code for this one would be 0, A. And actually, you know what, I don't have to do anything else. In this case, it's even the first step will tell me that there is definitely a way to do better, right? So I don't even have to go beyond this single step. I can compare these two, and I can find that this actually is smaller than that.
Smaller pattern.
So that's it. I know that this pattern cannot be canonical. Because there is some way, because I know ultimately I'll cover the whole graph, right? There are many different depths of trees. So this is the advantage we have, that actually when things are not canonical, it's sometimes very easy to prune them, right? So basically in this case, in one step I can tell you that it cannot be canonical. So the first time you find a violation, you stop. Essentially that's the idea. Okay? So in this case it was easy to find the first step. So I can actually throw this pattern out. So that's essentially the reasoning we adapt. Of course, let me give you a little bit more, so in this case it was easy to find out the smaller one. But what about the other one? So this one would be, supposing I start with this one, the AAB, right? So this is the other pattern. So the AAB. Okay, is this canonical or not? Right? So this was the second pattern here. And we said that that's also, I'm sorry, not, yes, this one here, AAB. So I want to compare this. I said this is the canonical form, this is not. So this one will take a little bit more work. So you have now AAB, this is 0, 1, 2, and the tuple is 0, 1, AA, 1, 0, 2, AB, right? So this is fixed. So the question is, can I find a lower, can I find a more canonical or a lower order? So write this down, AAB. So what if I start with this 0, right? Then this would become 1 and this would become 2. And then this code would be, so the first code would be exactly the same, 0, 1, A, A. That's exactly the same as that, so we can't do anything, right? This would be when I just go from here to here. But now when I go from here to here, I get 1, 2, AB. Okay, and now I can compare these two codes. Okay, so I can compare this and this. And because it begins deeper in the tree, okay, so look at the first number. Everything else is the same except the first number, right? But what does this number tell me? This says that this number is smaller, meaning it's higher in the tree, and this depth is lower in the tree. So we say that if you're deeper, you are smaller. Okay? So this is the, I mean, you can define any ordering you want. Really, if you wanted, you could have said that this is smaller than that, but you have to respect that same ordering each and every time, right? As long as you're consistent, you'll be fine. The whole point is that there should be one and only one unique solution, and you are free to choose whatever order you want. So I'm just choosing the order that deeper is better than a branch structure. So 1 comes after the 0, that's why this is preferred. So we'll say this pattern is smaller. So that means I found a violation, I found something smaller than this. So then I said this is not canonical. So you can eliminate things. If you're not canonical, you eliminate. And so, of course, this pattern is 0, 1, 2, and this will be the least one, which is exactly the pattern here, the AAB. AAB will be exactly that pattern, 0, 1, 2. Right? So the deeper one, the preferred. So I've already told you the intuition, but mathematically you can do this, systematically, and so on and so forth. So now, I can quickly just wrap this up because there's one key thing that was missing so far. There are no loops. Okay? And in a graph, the loops are what basically kill you. Okay? Because if it's just a tree-like structure, it's easy to do. So the cycles are what really matter. And so far we have not seen any cycles. So I'm going to pick this pattern as an example and see how we can expand the cycle. So let's say AAB. Now, let me ask you, what are the possible extensions here? So how can I extend this pattern? So in the depth first numbering, this is 0, this is 1, this is 2. So again, we want a systematic generation process, right? So obviously, I can extend from the 2, I can extend from the 1, I can extend from the 0, but there's a fourth possibility, which is I want to add one more edge.
Loop from 0 to 2 or 1.
Exactly. So I can add a loop. Okay. So now you have that choice. Okay. So there are actually 4 ways of doing this. The first one is you complete the loop first. Okay. This is, and we actually order them in this way, that any loops have to be finished. You cannot add any new edge before you added all the loops. So this is my first, and I'm going to deliberately put an arrow to denote the fact that this is a back, it's not a depth first tree anymore, right? So all my loops will be with a back arrow. So the depth first tree is still going to be this one. This is my depth first structure. This will be labeled 0, this will be labeled 1, this will be labeled 2. But there is a new edge, but it just happens to be a backward edge. Okay, so we say there's a forward edge or there's a backward edge. A backward edge is always a cycle. All forward edges go to new patterns. So this is the least or the first extension. Now remember I told you I want to go depth first. So that means you should do an extension from the 2 as your next. So that's my next set of choices. I can do A, B, and there are 2 choices exactly. So either it's BA and BB or BB. Actually there should be no error. Okay, those are the 2 extensions from node number 2. So this was node number 2. Okay, so we're now done with that. That means now I can go to node number 1. Right? So every time I do this, so remember in terms of the ordering, I'm going to sort of worse and worse pattern, so to speak, because my depth is decreasing. Every time I do this, my depth decreases in some sense. The depth of what I call the rightmost path. Okay, so the rightmost path, here the rightmost path goes all the way to the child. If I do an extension from 1, what happens? It will be A, B, but now this will be B in A or A, B, B, right? See, the depth here is smaller than the depth here, right? So it's a little bit worse of a pattern from the point of view of the ordering. I mean, we have to count everything, but I'm just telling you there is a systematic ordering among the patterns also. And that's the order in which you test them. So this is how the new pattern will be. And finally you go to the the root, because that will be the worst possible pattern in some sense. So these are all extensions from the A, which were extensions from depth 1. Finally you do the 0. So there are two choices from there. So that will be A, B, A, and A, B, B. So these are all extensions from 0. But so this is the whole process. Okay? This is how you basically go on counting. One other point I want to show is that this is just sort of to complete the whole thought. The extension, okay, and this is the key point. The extension, the next extension, this whole idea applies only to the rightmost path. Okay, so this is the key point of this algorithm, which is the G-span algorithm. So the one I've told you right now is the G-span algorithm, which is one of the most efficient methods. This is from Professor Jamia and Shifeng Yang's group in Urbana-Champaign, University of Illinois. But the main idea here is that the extensions only happen on the rightmost path. Okay, so what is the rightmost path? The rightmost path is with respect to the depth first, with respect to the DFS tree. So in this case, the rightmost path happen to be, it is the same path. Okay. So the next time you'll do is you'll complete the loop from this A. That means if you want to extend this, you have to complete this loop by adding it to things before, right, like that. Okay, so the rightmost path is there. The rightmost path here is actually, this is the rightmost path. Okay, so this extension only happens on the rightmost path. So this is one of the sort of interesting systematic growth of the pattern. You don't try all extensions, you only try extensions from the rightmost path. And every time you follow the same idea, that you complete the loops, then you go forward, okay? But you go only forward from the rightmost path. What is the rightmost path here? It is actually, this is the rightmost path. So you see that the rightmost path keeps on shrinking the higher up you go. And that's why you're more likely to find a non-canonical pattern as you go higher up in the tree. But let me just, finish this idea of rightmost path. So if I ask you what are the extensions of this, what would they be, right, from the rightmost path? First thing is, apply the same idea. Complete any loops from the rightmost node. So actually, if you want to extend this, let me do this in red. The extension of this would be, start from this node, okay, and add any loops if you can. In this case, a loop can be added, okay? Then you can add something here, then you can add something here, then you can add something here, okay? So it's the same thing. So finish all backward extension, then start with the forward extension. And that's how you keep on going. And every time you do this, you have to do the subgroup. So I haven't really talked about the subgroup isomorphism part, okay, which is how to do the matching. But I think you pretty much have to enumerate lots of things and then count them. So this is the key point, that how to eliminate duplicates, systematic generation, and then do the counting. So this is we'll take a break now. And I think we have time for discussions and things, or
15 minutes break.
okay.
Then we can
Okay, so we'll take a 15-minute break, and then we'll do the